Yeah.
Trieste.
Mm. Okay, so maybe we can start. Okay. So welcome everyone. It is my great pleasure to have Federico Sau, the speaker of today from University of Trieste, and he's going to talk about spectral gap for the symmetric inclusion process. Federico, the floor is yours. You can start whenever you want.
Okay. You hear me all well, and okay, thank you, Chiara, and also Patricia for inviting me. And it's a pleasure for me to give a talk here, and also I see some faces, so it's nice to see you here, and thanks. So, okay, today I'm going to speak about a joint work with Seonwoo Kim from Korea, and about spectral gap of the symmetric inclusion process, and yeah. I'm motivated to be a version of Aldous spectral gap conjecture for the symmetric inclusion process. And the talk is going to be, let's say, elementary, and also the result will be essentially, let's say, elementary, but I hope that you like the result. It's nice. So, okay, let's start from the basic. Okay, now it's working, and about what is the symmetric inclusion process. Many of you are familiar with it, but okay, this is just what the symmetric inclusion process will be for us today, a conservative interacting particle system on a finite graph. And then there will be particles hopping, depending the rates, depending on some geometries, some weights, which I will now describe. So the geometry is, as I said, just a weighted graph, weighted in the sense that we place symmetric conductances on the edges. It's a connected graph. And also we put some positive side weights on each side, alpha of x. Then we just describe the particle configuration with some variables eta of x, we describe the number of particles at x, and then we use the variable k to say that we have a particle configuration with k particles. And then what's important is the Markovian dynamics, which we impose on the system, which is described by the following infinitesimal generator. And we can describe it as follows. So there's only one particle jump at the time. And jumps rate are due to different mechanisms. And the particle, let's say we observe a particle jumping from x to y due to first an independent type of jumps occurring with in a proportional way with conductances and the alpha parameter associated to the arrival site, alpha y. And there is a symmetric type of attraction between particles, which is again proportional just to the conductance involving the two sides at which we are observing the particle jumps from and to. Okay? Please feel free to interrupt at any time if there are any questions. So very quickly, a brief background about the symmetric inclusion process in the form in which I presented it, more or less was introduced by Giardina, Cruce, and Reddy in 2007, and as a dual of some energy process exchanging energies. It's not very important for the talk today, and but what is more interesting, I find, for the talk, for the purpose of the talk, to distinguish it from its many relatives. So first of all, the very trivial one is the independent random walks, in which essentially you recover independent random walks if you forget about the attraction between particles. Then a very important relative of the symmetric inclusion process is the symmetric exclusion process, in which, also known as set, in which all the alphas are set equal to 1, and then the attraction part is just a -1 instead of a +1 in the eta variables on the arrival site. And then of course, you observe just at most one particle per side because of the form of the rates. And yeah, this also explains the name inclusion versus exclusion. Another important relative is the Moran model with parent-independent mutation from population genetics, which for those of you who know it, they already know it, but okay, we can recover it just by looking at the mean field version of the symmetric inclusion process. For instance, set all the conductances uniformly homogeneously equal to 1. Therefore, we can also view the symmetric inclusion process as a spatial version of an n-type Moran model with mutation. And then, in the same way in which there is a Wright-Fisher diffusion, which is a continuum analog and a diffusion analog of the Moran model, then there is also a diffusion analog of SIP. So there is what is known as Brownian energy process, which can also be viewed as a spatial version of this Wright-Fisher diffusion. I will speak more about it later. So unless there are questions, let's go on for now. And yeah, something more about the symmetric inclusion process. It exhibits some interesting qualitative behaviors. For instance, duality and graphical constructions are known for this process. Current limits have been studied. Also, Boltzmann-Gibbs principles. Also, there is a quite good knowledge on non-Euclidean long-range correlations. And yeah, these are some authors that work on this process. But also something very interesting I find is the phenomenon of condensation and metastability that this process exhibits. And here also, so essentially the list of authors who explore this regime, which corresponds to the fact that if alpha represents the mutation rate of the particles of the individuals, then these condensation metastability regimes are obtained when alphas are sent to 0. Okay. We will go back to this also later. So for the purpose of the talk, our main focus will be something. So what I just presented are somehow qualitative behaviors of the symmetric inclusion process. We're going to speak about some quantitative aspect of it. And yeah, it's a fact that since we are, by the way we define the dynamics, the graph is connected, the process is irreducible. So there exists in particular a unique stationary measure, which has this form. It's not very important for the talk. But what's important is that this measure is actually reversible. And therefore, by standard ergodic theorems for Markov chains, we will observe a convergence of the law of the process as time goes to infinity to the reversible measure, unique. So what we are going to speak about today is a quantitative aspect of this convergence. And today, I mean, actually what is known so far is just the spectral gap, which will be the main focus of the talk, which we're going to call as gap kg alpha, for the spectral gap of the K particle system. So I said I wanted to be elementary in this talk, so let's just recall why we associate, what is the spectral gap and why we associate it to convergence to equilibrium. Since we are in a reversible situation, gap has two interpretations, a spectral interpretation as the smallest non-trivial non-zero eigenvalue of the negative of the generator. And this is the first block. While the second block is also the optimal rate of exponential convergence to equilibrium when starting from any initial distribution and at any time. And okay, this is just, if you want, a formulation of the spectral gap, this last one, which is connected to convergence of equilibrium in integral form, and you can also express it in a differential form by differentiating this expression here over time, and you just write it as the optimal lambda, the largest lambda for which you can solve these functional inequalities for all observables of your system, essentially. Okay, and here I use the notation bar alpha k is the variance of the k particle system with respect to the equilibrium measure, and E alpha k is the Dirichlet form evaluated at F. Okay, this is notation. And okay, let us recall a bit the parameters of our system. So n is the size of the graph, c, x, y are the symmetric conductances, and alphas are the site weights, and k is the number of particles. And our goal is to estimate the spectral gap for the k particle system on any geometry. And since we are in a general non-asymptotic setting, we need to find a way to estimate this, and it makes sense to compare it with the one particle system, with the k equal to one particle system. Why this? Well, first of all, because, okay, for k equal to 1, as we said, there is no interaction, so there is just one particle. It is evolving then essentially just like a random walk on the graph. And the gap of the random walk on the graph is an important quantitative feature of the graph. And nevertheless, okay, in general situation, you have no hope to have anything explicit about it. And it's an eigenvalue problem. So in general, no way to solve it explicitly. So the idea is, what we expect is to compare these two things. So compare the spectral gap of the k particle system with that of the single random walk on the graph. And what to expect about this? So example number 1, the very trivial scenario, that of k-independent random walks, in which it is well known that in absence of interaction, both variance and Dirichlet form perfectly tensorize. Therefore, everything tensorizes, and the spectral gap of the k particle system then equals, for any k, the spectral gap of the single random walk. And this, in PDE's language, is the fact that the Poincare constant is dimension independent, if you want. However, as soon as we look at truly interacting systems or truly interacting components, this exact tensorization breaks down, the one of the variance in the Dirichlet form. Therefore, there is, I mean, this identity between spectral gap of the k particle system and the random walks is not really expected to hold. An example of this is, for instance, for those of you who are familiar with the zero-range process. Of course, there are many zero-range processes, but take the one with unit rate, and there are results by Morris and then by many other people, and improved recently by Hermon and Saleh, which prove essentially up to a universal constant the fact that the k particle system of the zero-range process can be compared to the spectral gap of the random walk, but up to some factors which depends both on k and n. Okay, and okay, and so it makes sense to, so for sure there will not be such an identity in this case. However, there is this outlier, let's say, in this family, in this class, which is the symmetric exclusion process. And why this? Because okay, Aldous from the early 90s, let's say, also it's well known to be also arising from conversation with Diaconis, came up with this conjecture, which took his name, or the fact that the symmetric exclusion process, and actually more general process, the interchange process, satisfies such an identity for all k and for all graphs. So the random walk of the exclusion, the spectral gap of the random walk on a graph is equal to the spectral gap of the exclusion process for any k. And so this stayed there as a conjecture for more than 20 years, for around 20 years, and many partial results came out. And until 2010, 2009, Caputo, Liggett and Richthammer established the conjecture. So this was eventually true. It was proved to be true, and the proof combines two main ingredients. The first one is a nonlinear network reduction, which allows somehow an induction argument on n, the size of the graph, and to prove a hard correlation inequality, which became known as an octopus inequality. And why am I spending time on this? Because if you look about SIP and the fact that these two processes somehow they are related, both these two aspects of the proof lack of an analog for SIP. And this is because essentially, in one word, there is no clear particle-hole symmetry that is nicely exploited in the work of Caputo, Liggett, and Richthammer. And there is no particle-hole symmetry for the SIP, for instance. And then also, along these lines, also recently was proved the same conjecture, the same result, the same identity for an open, non-conservative version of the symmetric exclusion process in equilibrium. So a reversible symmetric exclusion process by Saleh. And this proof is also very nice, and it is only based on a property which is called negative dependence, which is some sort of negativity of all correlations of all orders. And yeah, if you look at SIP, then essentially we have exactly the opposite property. So SIP is, if you use the same language, is really positive dependence. So it has positivity of all correlation of all orders. So in a sense, the argument used there also doesn't have a clear analog in the context of the symmetric inclusion process. The third relative, the Mora model, which was this mean field version of the symmetric inclusion process. If you look at it, we hope that somehow this could give us an idea of what's happening about the spectral gap of the general symmetric inclusion process. And yeah, I would like to convince you that actually everything is known for this mean field version and is also fairly easy. And actually, if the full eigencomposition for this for the generator of the Mora model is known and actually is fully explicit since the 70s, and the eigenvalues are these ones, without counting multiplicities. And in particular, if you just plug in L equal to 1 in this display, then you recover exactly the Aldous spectral gap conjecture for the Mora model. And yeah, if you want just a quick overview of what almost a proof could look like, it's very, very easy. The idea is, okay, believe me that you can focus your effort in looking for to solve the eigenvalue equation just for functions satisfying this identity for all xi, which are particle configurations with k-1 particles. And then essentially, just by writing down what the action of the generator is on these functions, splitting up this difference and summing up things here. And for the second term, just remembering the property I told you at the very beginning, you essentially can close without any effort your equation in terms of just the value of f at theta. And so you recover exactly, you solve it really like explicitly like this. So as you can also extrapolate from this almost a proof is that essentially there is a lot of symmetry. So you haven't found just an eigenfunction, you found all the eigenfunctions in this way. All eigenfunctions satisfying this condition are eigenfunctions for the generator, and you know what the associated eigenvalue is. However, I showed it also to say that as soon as you drop the mean field assumption, the tricks I quickly try to explain to you, they break down immediately. So of course there is no way to proceed in this way. And okay, just to introduce also something that we will need later. I mean, the history about the eigencomposition of the Mora model was known since the 70s. It actually was known for the continuum analog, the n-type Wright-Fisher diffusion with mutation, which has exactly this form. Yeah, it has been generalized. I mean, it's known for actually many more models than just the Wright-Fisher diffusion, but it's always very crucial to have a complete graph structure underneath. And yeah, as soon as you know, for instance, as soon as you know some eigen compositions for either one of the two models, then you can actually hook up, use what is known to be an intertwining relation between the continuum and the discrete model, where pi is this intertwining. And as soon as you have, for instance, this intertwining relation, what you can do is just to transfer all the spectral information you have from, in this case, from the particle system to the diffusion. And if you have a sort of inverse intertwining, you can do also the other way around, of course. And okay, so there is no hope to really use this information, the spectral information, for the symmetric inclusion process, because we are not in such a nice symmetric situation. However, the intertwining relation is something that we should keep in mind, because it's something which is much more general than just a complete graph, and also holds in the graph context. So as soon as you, okay, we have a spatial SIP with some conductances, which corresponds to the conductances of the underlying graph. We can also describe diffusion, interacting diffusion, which takes into account also a graph structure by imposing these conductances. And then the intertwining relation holds between these two continuum and discrete model. So as soon as we have some information about the gap of the particle system, we transfer it back to the information for the gap of the diffusion and vice versa. And okay, just a comment, this correspondence between results of one system to the other, of course, is not true for other properties and quantitative features of the system. But we can still use it because we are looking at spectral properties of the process. Okay. Having said that, if there are no questions, we are finally ready to state our main results, which, okay, introducing some notation, gap SIP to be the infimum of the gap overall truly interacting systems. So k is larger or equal than 2 because we want some interaction. Then our result is that for any graph and for any positive weights, we have this sandwiching of the gap of the symmetric inclusion process with that of the random walk. And here, as an upper bound, you have the gap of the random walk. As a lower bound, you have this extra factor here, where alpha mean is just the minimum of these alphas. And of course, as a corollary, you get, as soon as alpha mean is larger or equal to 1, then actually this version of Aldous spectral gap conjecture holds true for the symmetric inclusion process. So, okay, if we go back now, if we, okay, now look at exactly what I told you. So transferring this information from the particle system to the diffusion, then we record we have the Brownian energy process, which has this first infinitesimal generator, the symmetric inclusion process, this other infinitesimal generator. We have the intertwining relation, as I told you. Therefore, we have exactly the same result for the continuum model. In particular, also this kind of Aldous spectral gap identity holds for the Brownian energy process, as soon as alpha mean is larger or equal than 1.
So,
yes,
Federico, may I ask you some questions?
Absolutely, yes.
So first question is, for me, it's a little bit surprising, this result, because, I mean, in principle, attraction should prevent equilibration instead of help equilibration, no?
Yeah, in a sense, yes. In a sense, yes. Of course, I mean, by moving, I mean, playing with the alphas, you also your equilibrium will look different, no? So in a sense, the greater the alpha, the more things will look like independent random walks. The smaller the alpha, things will look like piling on top of each other. I will comment now what about this threshold, but So this threshold is not very surprising in a sense, and I will try also to explain why.
Okay, and so maybe I'm spoiling something, but the invariant measures of Webb are some sort of log gammas, or no?
Products of gammas, yes.
And these guys are log-concave if alpha is bigger than 1. Is that the thing?
Exactly. So alpha mean greater or equal than 1 corresponds exactly to the case in which we are in the regime of log-concave reversible measures, both for the symmetric inclusion process and for the Brownian energy process.
Okay.
Exactly.
Okay. Thank you.
Yeah, Milton anticipated a bit also like some comments about this result. So let's go one by one through it. So this threshold alpha mean larger or equal than 1. So in a sense, look at the generator. If we understand like the influence of each particle corresponds to the value 1, because we have here just the number of particles, so there is a factor 1 in front. The regime alpha mean larger or equal than 1 corresponds to the situation in which the influence of independent diffusion somehow is at least as large as that of the particle interaction. And in mathematical terms, if we look at the stationary situation, this really corresponds to log-concavity of the reversible measure. What about alpha mean? What can we say? So first of all, if you look at our proof strategy in which we use comparison techniques, as I will try to then quickly overview in a few minutes, our proof breaks down. And however, if we look at, if you do some inspection with small values of n and k, the identity, the spectral identity still holds, seems to hold. And if we want to anyway use the result also in the regime in which alpha mean is smaller than 1, the nice news is that you can get bounds which are independent of both n and k. So you can use it, for instance, for scale limits, as long as you don't have any degeneracy of alpha mean to 0, of course. And about this specific asymptotic regime is intrinsically connected, as I anticipated, to the metastable aspect, to the metastable picture of the symmetric inclusion process, which is completely described in these two papers. And let me try to explain it also very briefly. So in the regime in which, for simplicity, we take all the alphas to be constant and going to 0, and assuming something about that the particle number of particles should not grow too much compared to alpha, then if we look at the symmetric inclusion process on the time scale 1 over alpha, then what we are looking essentially is the evolution of all the particles sitting on the same site piled together, and then their position, their common position, will be evolving like the random walk on the graph, exactly on the same graph. And this is exactly the picture very specific to the symmetric inclusion process. Then the reversible inclusion process has different aspects, different time scales, etc. But for the symmetric inclusion process, actually, this is the only metastable scale. And so putting all the things together and the fact that the gap of the random walk, if we look at a situation in which alpha is going to 0, is of course proportional to alpha, of the same order of alpha, then somehow it's natural to conjecture that since there are not other time scales, that the spectral gap of the symmetric inclusion process should be of the same order, again, at least of the same order of that of the random walk as alpha goes to 0. While our result, because of this extra alpha mean factor, can only ensure like a square root, a square of the gap on the left-hand side somehow. So yeah, this is a bit the situation, some very rough heuristic of what's happening here. Okay, then last comment, which maybe it's interesting for somebody, is that, okay, if we recap some older versions of Aldous spectral gap conjecture, which hold when I refer to Aldous spectral gap conjecture and versions of them, I refer that they hold all graphs, not on specific graphs. We know that this identity holds for independent work, exclusion process, the reversible version of the exclusion process, the binomial splitting process, as we proved with Matteo Quattropani in a recent paper, and now also for the symmetric inclusion process and the continuum analog in this regime of alpha. So one may wonder, okay, since all these processes Chiara knows very well, they enjoy all this property known as self-duality, duality, different forms of it. One may wonder whether, okay, there is somehow a connection, or maybe there is a meta theorem which says, okay, as soon as you have duality, self-duality, then this relation must hold. And fortunately, from my point of view at least, is that there is a counterexample for this, which is was mentioned in a paper by Caputo, Labella, Kwan, in which they take what with this notation may be called as an instantaneous thermalized version of the Brownian energy process in a mean field setting on the complete graph, and for this process, this spectral gap identity does not hold. So it's not something that can be, there is any hope to derive it from duality or self-duality per se. Okay. So in the remaining time, how much time? Yeah, plenty of time. So I will try to go like to give to quickly sketch the proof of this main result. First, the upper bound, which is the easy part, and the lower bound, which is slightly more involved and needs a couple of more arguments. In particular, I will tell you where we use comparison techniques. Okay, for the upper bound, the only property that you really need, and this is something very general that you can really say, okay, as soon as you have some sort of duality, self-duality, you should have this upper bound, and this is very easy, is in the form of what we can call what is known as consistency, which corresponds to the fact that there is somehow an equivalence between these two procedures, which first, it's the same if you do the following: first evolve k particles and then remove one particle uniformly at random. Or you can do the other way around: first remove one particle uniformly at random and then evolve the remaining k-1 particles. And if you look at just the level of finite dimensional distributions, these two things are equivalent. And this is a property which holds for SIP and for many other models. Actually, all of them, essentially all of them I presented in the previous slides. And yeah, if you want to view these in formulas, then...
So may I ask you a quick question?
Absolutely.
Sorry for interrupting you.
I'm happy.
So, yeah, I mean, for all the other models that you just said, you mentioned, this consistency property is just basically what we call basic coupling, no? So you put you can couple the system with k-1 particles and k particles at all times, and then you can do two things at the end, which is one is forget about which was the target particle, and the other thing is just at the target particle. So these two procedures are the same. So, but for SIP, it's a little bit different.
It's a bit trickier, yes, because yeah, if you do it with these zero range with monotone rates, then it's very easy. I mean, it's very classical what you should do. But for SIP, it's very fundamental, crucial, the fact that you do this uniformly at random. So if you don't do this uniformly at random, it's not absolutely, it's not true. So you cannot just tag your particle at first and then remove it either at the end or at the beginning. You will not see the same thing because it also influences the other particles. A way to look at this is to do one step back and to, let's say, if you want to view it graphically, you just observe that somehow the symmetric inclusion process, just like the Moran model, has a look-down type of construction. A look-down construction is the one in which you label particles, and the interaction, so the fact that one particle jumps to the site of another particle, is only allowed if the label of the particle is higher of the one that it wants to jump to.
Okay.
But you do this instead, this attraction type of interaction, you do it at a double rate. Instead of doing at rate 1, you do it at rate 2. And then if you do this, you have something which is graphically consistent in your sense. So the top particle will only look down and the ones will not look up. So you can always remove it at any time and you will not change the configuration below. But the nice thing is that if you then do a uniform relabeling of particles, you observe the SIP. So that's why this consistency property holds for the symmetric inclusion process. But because this uniform removal of a particle corresponds to remove the top one when you do a uniform relabeling. And so, yeah, somehow, so this thing, you don't need this uniform at random when you look at the interchange process, independent random walk, zero range, but it's crucial here.
Okay, thank you.
Yeah, sorry for the long answer.
No.
Okay, so yeah, and this thing is something that in formulas you can write it as a commutation relation with this particle annihilation operator. Okay, it's just if you know it already, it's boring, but it's nothing like up to normalization. This is just an average of your observable when you remove at random a particle. And the nice thing is that as soon as you have this commutation relation, then once you check that this operator is non-degenerate, then you have an inclusion of spectra. And trivially, then by setting L equal to 1 in this expression, you just recovered the infinitesimal generator of the single random walk. So you have this nice embedding of spectral as the number of particles increase. So in particular, you have the upper bound. Okay. A lot of time for the upper bound, but okay, the lower bound, we can use some information about that because, okay, we have this embedding of spectra. So what we are left to prove is to understand what are the remaining eigenvalues which are not contained in all the other ones. And so somehow this allows us to do an induction argument on K this time, not on N. We will not touch N. And okay, also because the generator is self-adjoint, we are in a reversible situation. We can do, it's very natural to do an orthogonal decomposition of the underlying Hilbert space into functions which somehow can be lifted from functions which are functions actually of only K-1 particles, and its orthogonal complement. And we'll call them like this. It's natural to, I mean, there is a reason why we call it like this, and this is the kernel of somehow the adjoint of the annihilation operator, which we call particle creation operator, and it is defined exactly in this way. Yeah, and as soon as you do this decomposition by very standard arguments, so we can set an induction on K. So this minimization problem, you can really split it in by minimizing on these two orthogonal subspaces, and therefore we are only left to check the inequality, the inequality just for functions which belong to this the kernel of this creation operator for K assuming that it holds for k-1. And yeah, as a second step, we need to rewrite the Dirichlet form. And okay, by using also a similar decomposition used for the zero-range process by Hermann and Saleh in 2019, we can rewrite it in this way. So where now we are writing the Dirichlet form of the k-particle system as an average over k-1 particle systems of the Dirichlet form of a perturbed random walk, perturbed exactly by alpha plus the k-1 particles, which we are averaging with respect to. So we view this function f as a function of just the remaining kth particle. And an important step is to say, okay, just do a crude bound now at the level of this Dirichlet form of just a single random walk for the perturbed random walk. And thanks to the fact that f, we choose it f to be in the care of this particle creation operator, this what is left essentially is the variance of this observable f. And the fact that we are not losing this factor k is very important, and it survives just because we are really selecting correctly the test functions. And once we have this, we are essentially now we are in this situation in which we bound the Dirichlet form from below by this quantity. And let's look now at this parenthesis, this quantity in parentheses, which is an inf over the perturbation. And by using something that's slightly more sophisticated than just the spectral gap variational formulation, use a min-max type of eigenvalue theorem, a current min-max eigenvalue theorem in a, let's say, by comparing things. And for this psi perturbed random walk, and what you get is this bound, where you see that alpha min pops up, and also the factor k enters. And if we just leave this thing like this, you see that this k in the denominator, if we take k larger and larger, is telling us that perturbing, like adding some positive side weights to the arrival side for a single random walk, looks like the spectral gap may also degenerate, which is a bit counterintuitive, but actually this estimate is really sharp. So it's true that if you add, let's say, if you increase your alphas, even though it looks like you are speeding up your process somehow, but if you do this in a non-mean field geometry, and if you're doing this perturbation in a non-homogeneous way, you really can worsen and worsen your spectral gap. And this is essentially the exact order at which you're doing this degradation. So this estimate cannot be improved. However, it's very important that we had this factor k left, because as soon as we put together these two these two inequalities, there is an extra factor in the numerator, which with let's say it's a small magic, and then you really get this factor uniformly over k. And this is how we essentially collects all the proof of the result, and I think also this concludes the talk. Yes.
Many thanks, Federico. Let's see if there are questions or comments. So I wonder if you have any conjecture for the non-conservative inclusion.
Thank you for.
You expect the same sandwich?
Yeah. So yeah, I received a question last week from Paul Clebon, and yeah, the same approach. We have all the ingredients to prove this exactly same result for the reversible, of course, in which we have the spectral characterization of the spectral gap. Mm-hmm. So the proof is a bit different, but you can use the same comparison ideas also there.
Let's see.
So I have a question. Could you come back one slide, please?
Yeah.
So when k, you have this factor, no? So when k goes to infinity, that factor goes to alpha, basically,
Yeah.
right? And when k is equal to 1, this factor is also alpha.
When k is equal to 1 is 1.
Oh, yes, 1. Sorry. Yeah, you're right. So that means, let me see if I'm correct. It means that depending on whether alpha is bigger or smaller than 1, adding particles helps you or speed the process, or helps you or makes the process slower.
So if we add a matching upper bound when alpha is smaller than 1, matching this alpha mean, I would say yes. There is still some space, so.
Oh yeah. I mean, I'm not talking about I'm trying to understand what is going on with the dynamics, though. So not really.
Okay.
So maybe one can prove those things later, but I just want to see if I want to see if this is the right intuition or not.
So alpha somehow, yeah, with this induction on k, so the larger k, so yeah, so with this estimate here, so if alpha is too small, so let's say alpha min is more than 1, then each particle will be slowed down by a factor alpha min. And so you cannot, with this extra factor here, you cannot recover it full, yeah, in a sense, yes.
Okay.
So the thing is that if you do exactly the same analysis for instance, for independent random walk, the sharp estimate here, if you ask f to be in the care of some of the corresponding particle creation operator, the correct estimate is k. So I mean, this degeneration is, yeah, so it's pessimistic in a sense. So it's too uniform, I would say, yes.
Let's see if there are other questions.
Yes, Federico, I was wondering, so the Aldous conjecture, it was not only about the exclusion process, but also about the interchange process. So is there any way to, well, yes, do you have a version of your result that would be true for a version of the process where the particles are labeled? Okay, so I mean, first, does it make sense to consider such a process? And
for the labeled part, you can, of course, you have a non-labeled particle system. You can look at the labeled particle system. I believe that as we were discussing before with Milton, so there are many ways in which you can, like, for instance, the look-down construction, so you can have a labeled version and then do something strange with the label and recover SIP, but the labeled version, I mean, there are many labeled versions for the same unlabeled thing. Okay. So the most natural one would be just put just labels and then they interact symmetrically. And for this, yeah, the same arguments should hold. But if you're thinking more about so the problem is that you cannot really have the something which is in which the parameter k does not appear, as in the interchange process, no? Because there is not this clear particle hole symmetry for the symmetric inclusion process. So, like, you can label all vertices of your graph. So you have, instead of k, you have just the parameter n, the size of the graph, but anyway, for the symmetric inclusion process, the parameter k should always be.
Oh, sure. But you would have okay, so some kind of result that would be like for a labeled exclusion process. Okay, so here there is more than one natural way to label the particles in a Markovian manner.
Yeah, exactly. Yeah, this look down and just a symmetric in which you are a particle and you want to jump.
Yeah, okay, so if you construct the dynamic with k minus one particle and a tagged particle, then the tagged particle will not have a. Then this will and iterate it. Then this is not symmetric.
This is not a symmetric. Well, yeah, the tag particle depends if you want it. Yeah, depends on the type of dynamics you impose on the tag. So if the tag can be influenced but cannot influence the others, then you need to do something about uniform relabeling or play with the labeling to recover the symmetric inclusion process.
Thank you.
Yeah, thank you.
Let's see if there are other questions or comments. No, it's not the case. So let's thank Federico again. And we update next Wednesday. Many thanks. Bye bye, everyone.
Bye.